We're starting with question 1. Here's figure 1. And you're given some numbers and asked to calculate the force between big Q and little q. And you're given a distance and the magnitude of each charge. So you're going to use Coulomb's law to do that. So go ahead and do that. You might as well do it for your own problem. I'm going to do it for this problem and show you what I get. Okay, so using my numbers, you see I wrote down Coulomb's law. Okay, the two charges and the distance between the charges squared. And then notice the formatting. I wrote everything out, 10 to the 9th, 10 to the minus 9th. You have to be in standard units, the two charges, and the distance in meters. Notice I did the units cancellation. There's Coulomb's canceling Coulomb squared, the meter squared canceling meter squared. That would leave units of newtons, but since the unit given is micronewtons, 10 to the minus, whoops, that's a mistake. I should take out the 10 to the minus 6 because it is micronewtons. So that doesn't belong there. I'm going to erase that. It's 28.558 microunits, and then rounding to 3 significant figures, I get 28.6 micronewtons. Okay, now we want to consider the energy associated with this arrangement. So we think of this charge as having energy because if we released it, it would gain kinetic energy. So it's going to go off in this direction because there's a force on it, accelerating and gaining kinetic energy. So there's a kind of electric potential energy associated with this position. And it should be clear that if the charge is further away, it's going to have less energy than if the charge is closer. And the two ways of thinking about it is, if I release the charge from here, it's going to gain a certain amount of kinetic energy. If I moved it closer to, say, point A and released it, it would have more energy and gain more kinetic energy. Also, if I move this charge from its position to A, I would have to do work, whereas if I release it, it goes to position B without doing work or doing a negative work. And what we learned in class was, and in the introduction video, is no matter where this is, it's going to have energy unless it's far away. So keep in mind, or that leads to the convention, that the place that we consider the electric potential energy to be 0 for 2-point charges is at infinity. And the equation for calculating the amount of energy stored between two charges is derived by putting this charge far away, and let's just, for simplicity, move it in from infinity along the x-axis. So we're going to calculate the work it takes to bring the charge from infinity to whatever position, A, B, or the current position. We're going to integrate from infinity to that position. The force, right, the work equation is the force times the distance. So here's the force, here's the distance, and when we do this integral, the k and the q's are constants. We're integrating dx over x squared, and so we get x, or r. So out of doing that work equation, we derive the equation for calculating the potential energy between any 2-point charges, where r is the distance between the charges. And so this is the equation we'll use to calculate the energy for this situation. So I'm going to use these numbers to calculate what that energy is. So here's what I expect to see on the quiz, right? The equation, the numbers with the units, and oops, I didn't do the units cancellation. So notice the meters only cancel one of those meters, and the 2 coulombs cancel the Coulomb squared, so I'm left with Newton meters, which is joules. But because it's a small number, I have you report it in microjoules. So in microjoules, I get this number, and I round it to 3 digits. And this is the answer of the energy stored for these numbers and this charge arrangement. All right, the rest of the question is filling in blanks about energy, kinetic energy, work, the law of conservation of energy. I think I've discussed that as I've gone along here, so I'm going to move on now to question 2. So you've noticed these questions have a lot of text in them, and don't just race through the questions filling in the blanks. Read the text carefully. This is to prompt you to make sure that you understand the concepts behind what we're doing. So anyway, in question 2, the first calculation part is calculating the potential energy due in the hydrogen atom, and it's a negative energy, so that means it takes energy to get the hydrogen atom, the electron off the hydrogen atom, or to ionize the hydrogen atom. And so use this equation and do the calculation. Okay, this is a little messy, but there's the equation for the energy between 2-point charges. There are the units up there. And notice the electron and the proton both have this charge. So it's 1.602 times 10 to the minus 19 coulombs squared, because it's the same. And that's the distance between the charges. And this is the result you should get. And the units that are left are Newton meters, which are joules. Now in the lab you're going to learn about electron volts, because this is such a small number. So when we deal with the energy of electrons and protons, we use this unit of electron volts, which you'll learn about later. And it's the energy of 1 electron passing through 1 volt. So that's 1.602. And when I do the conversion, we get that this potential energy in electron volts is 27 electron volts. Okay, the next thing we want to do is take our test charge and put it 10 centimeters away, 20 centimeters away, and 30 centimeters away from the central charge Q, and calculate what are the energy at those 3 locations. And since the charges will remain the same, you can see that the energy any place the same distance from the charge will have the same energy value. So these are equal energy lines. If this were 10, 20, and this were 30, all values on that circle, which are equidistant from the charge, would have the same energy. So we're going to have different Q's, but I'll do the calculation for the Q that I had, which was 1.23 coulombs, and you can do it for your charge and see if you can get the correct values. Okay, here are the values I got. There's the equation, the numbers, the units cancellation, and that's what I got for 10 centimeters. And I didn't bother doing the calculation again because I know at 20 centimeters it's going to be half, and at 40 centimeters it's going to be a quarter of that number, the unrounded number. So those are the values I got. Now notice you have different values, but if we divide the energy we got by the charge that we used, then we get the electric potential for this, and we're going to get the same numbers. So calculate the voltage or the electric potential on those circles of 10, 20, and 40 centimeters. And you can do it, I'll do it 2 ways. I'll do it by dividing this by the charge that I used. You can do it that way. And then I'll also do it by using the general equation. After we divide out the Q, we would just have KQ over R. So I'm going to demonstrate that done both ways. So there you have it. If I take the energy that I calculated and divide it by the charge I used to calculate it, I get the energy per unit charge, 11.24 times 10 to the third joules per coulomb, or 11.2 kilovolts. You're going to get the same thing because you had a different energy and a different charge. So it makes sense to label those surfaces by the voltage because it's independent of the charge you put there. Also, if we just use the equation for calculating the electric potential for a point charge, this gives us the same result. So the equipotential surfaces have the same value in terms of electric potential independent of the charge that's put there. And so that gives us a value where we can now calculate the energy of any charge put there simply by rearranging the equation. So we multiply the charge times the electric potential of that line, and we get the energy for any charge that we put on that line. Okay, question 3. Look carefully and thoughtfully at these 3 diagrams. Figure 3 shows an electric dipole, field lines leaving the positive charge, entering the negative charge. The black lines show us the electric force field. The red lines are equipotential lines, lines of equal energy. So the red lines are showing us the energy field. This figure is pretty much identical, only the positive charge is here, the field lines go across. We're familiar with the shape of the field around a dipole. We're not so much familiar with the energy field. But what we do know is that the center line, because there's positive and negative energy, is zero energy or zero voltage. And these lines will be negative voltages and positive voltages. The other thing that's important is that these lines have to be perpendicular, because if you move around in a force field, you must move perpendicular to the field, otherwise the energy will change, right? If you move in the direction of the field with a positive charge, the energy goes up. This way it goes down. The only way it doesn't change is if you're perpendicular. So if you look at these diagrams, you'll see in most cases the lines cross perpendicular. Now, if you look carefully, you can see this one. It's not perfectly perpendicular. Okay, so that's all right, but it should be. This figure in particular is very poorly drawn. You see how these lines are crossing? They should be crossing perpendicular. So either the field lines are wrong or the equipotential lines are wrong. But they give us the general idea. Now, because this is negative and positive, and because the potential depends on the distance from the charge and the size of the charge, it's pretty clear that a position in the center of these 2 charges is going to be 0. And I'm going to write that out for you. But here, when we go to the center of these 2, the numbers are both positive, and so they're going to add. So let me write out those calculations and show you what it should look like if you were doing it on a quiz. Okay, here's the calculation. So the voltage at any position for any of these, since there's two charges, are going to be V plus V minus. Well, for those two, this is going to be plus and plus. And so if we do either of the dipoles, we're going to have K, Q over R. And on a quiz, write out the units. You see you have Newton meters squared per Coulomb squared. One of the coulombs cancels, one of the meters cancels. That leaves you with Newton meters over coulombs. That's joules per coulomb. That's a volt. So the units are correct. And the number I get for the positive charge is 130.9 joules per coulomb, or 100, rounded to 3 digits, 131 volts. Of course, the negative charge in figures 3 and 4 is going to be exactly the same but negative, and so the sum will be 0. But where both charges are positive, both of these numbers are going to be positive, and so the answer in that case will be 262 volts. I'm using the number that I was given. You're going to have a different number, so you'll get different electric potential values, but no matter what your numbers are, these two at the center will be 0. Okay, the last two questions say go to the right 32 centimeters. Well, this may not be right to scale, but we're considering this equipotential line at this point. So remember, once we calculate the value here, it should be the same anywhere else on this circle. So this distance is 32, this distance is 32, and we're going to this point. And it's the same thing over here. The distance between the charges is 32 centimeters, and we're considering, although it's not quite to scale, this line 32 centimeters over. So let's do that calculation for both of these. Okay, finishing up problem 3, so we're over here, 32 centimeters from the positive charge and 64 centimeters from the negative charge. To get the voltage at that point, we're adding two numbers, the positive charge and the negative charge. Those distances are now different. Notice when we do the calculation, this is 10 to the 9th, this is 10 to the minus 9th. They cancel. So if you do 8.99 times 2.33, that's the charge that I got, divided by 0.32, you get this. I didn't bother to do that calculation because I know it's going to be half of this. And the answer will be half of this because we're going to subtract half of this. And then for this one, everything's the same, only both numbers are positive. So we're adding those two numbers, and you should get that for your voltage. Well, it'll be different because your charge is different. And that finishes number 3. Okay, question 4. Let's just make sure we understand the figure we're looking at. So here's a positively charged plate. Remember, this is in 3 dimensions, so you're picturing this, 2 large 3-dimensional plates. One of them's positively charged, one of them's negatively charged, and so the field between them are a series of uniform lines. So we see the field lines are the white lines, and then there's a charge we're going to move around. There's a single charge that we're going to move around from A to B, D to C, C to D, and D back to A. So that's 4 displacements. And we're going to calculate the work done to move this charge through those 4 displacements. And since we end up back where we started, you might guess that the total work should be 0. So this is the work equation. This is the force. Since we know the field – and we know the charge, we can get the force. And the work is equal to this, but since we can find the force and the displacement, we can calculate the work this way. And here's another equation that is also useful at times, where the potential is related to the field in a situation where the field is uniform by this equation. And we will use this this week and weeks after in situations where we have a uniform electric field. Okay, let's do the calculations. Here we go. The work is the force times the distance times the cosine of the angle between them. The displacement. So we have the force is Q times E, d cosine theta. So the Q is the 2 millicoulomb charge. I changed this from kilonewtons to newtons, so that would be 1.5 times 10 to the 5th newtons per coulomb. And the displacement from A to B is 25, and we get this. Now when we go from here to there, that's 15 centimeters. The charge is the same, the force is the same. Whoops, I left out the cosine of theta. But the cosine in this case, since the displacement is this way and the force is that way, the cosine would be 90 degrees. And so that is moving perpendicular to the field, and so the work is 0. And if you move, so here I'm pushing the charge I'm exerting, okay, this could be confusing. Let's back up for a minute. I'm pushing the charge this way, and it's being displaced this way. So that's a positive work, right? I'm pushing a positive charge toward the positive plate. Logically, I have to push it. And so the displacement is this way, the push is this way. Here, the displacement is this way, but I'm still pushing in this direction, right? I'm holding the charge from going. So I'm exerting a force opposite the field to hold the charge. So the angle between the displacement and the force that I'm exerting is 90 degrees. And in this case, I'm exerting a force this way, right? Because I'm moving the charge. If I let go, it's going to go by itself. So I'm exerting a force opposite the direction of the displacement from C to D, right? Those green vectors are the displacement vectors. And so that's 180 degrees, and logically, if the charge moves in this direction, it does it by itself. That's a negative work. That's work being done on me. And moving it this way is the same as this displacement. It's 15 centimeters. I'm exerting a force this way to keep the charge from moving. And the displacement is down, and so the angle is 90 degrees. And so that's 0 work. Okay, don't get lost in the math. Clearly, I do a positive work to move it here. I do no work to slide it up there. A negative work is done on me when it moves this way, and then a work of 0 there. And so, as expected, if you go from a position through 4 steps and come back to the same position, the net work, the net displacement, and the net work is 0. So 75, 0, negative 75, and 0 add to 0. The next question is to get the voltage between the two plates. And so this equation, remember, this is only good when the field is uniform. That works in this case. So just use this equation to find the voltage between the two plates. Do that by yourself and then see what I did. Okay, that's what you should have gotten. Notice the units, newtons times meters, or joules per coulomb, that's a volt. And yes, it is a very strong magnetic field, and so it is a high voltage. It is 60,000 volts, or 60 kilovolts. At first you might think, oh, that's too big, but no, that's the answer in this case. So the last thing is to become familiar with this unit of electron volts. It's a unit of energy, and we use it when we move small charges like an electron or a proton around in a magnetic field. So if I move a proton this way, I would increase its energy. If a proton moved that way, it would lose energy. And we simply use the work equation to calculate it. If we put the Q in joules, we'll get in coulombs, we'll get the answer in joules. But if we put it in electron volts, in electron units, we'll get electron volts. The instructions explain that. So do those calculations and see what you get. Try it before you look at what I did. Okay, so calculate the energy using the charge times the change in voltage, the change in electric potential energy. And if we put the charge in coulombs, then we get joules, right? Because a volt is a joule per coulomb. But if we put the charge as an electronic charge, then we just keep the volts and we call that an electron volt. So you see the energy of an electron moving through this field is a very small number if we use joules, but if we use electron volts, it's actually quite a large number. So the reason we introduced this unit is because it's widely used in atomic and nuclear physics and in chemistry, because chemical bonding energies can often be measured in electron volts. Okay. Last question. Here are 4 charges. Now watch what I'm going to do. I'm going to, whoops, what's that? I'm going to arrange them into a square. So I move one down here, and there's no field, so there's no energy required to move the. But since there's a charge already present, it's going to take some energy to move this in from infinity to here. So let's calculate that energy, and if we call this Q1 and this Q2, we can call this U12. So here's the calculation. There's our equation for the potential energy due to 2-point charges. And since the charges are going to have the same value, I changed the Q1 Q to Q squared. So this would be the general solution. And now if I put the numbers in, 8.99, notice this is 10 to the 9th. Newton meter squared per coulomb squared. And then the charge that I was given was 1.12 microcoulomb, so that's 10 to the minus 6 coulombs. So notice that's coulomb squared, that cancels. There's 1 meter, that leaves you with Newton meters, which are joules. And just to make things easy, this is 10 to the 9th. When we square this, this is going to be 10 to the minus 12. So 10 to the 9th, 10 to the minus 12 leaves us with 10 to the minus 3, which is millijoules, which is what we want. So when I do the calculation, I'm just going to go 8.99 times 1.12 squared divided by 0.12, and I get this. And so there's my answer for the amount of energy it takes to move this charge into that position. Okay, now we have to move the second charge in. Okay, I saved that information up here. Now let's move the second charge in. Oops. And let's put it right here. Now notice when I move this in, the energy now stored in this is going to be the energy due to its position relative to this one and this one. So I got to calculate U32 and U31. There's going to be 2 terms. And it's worth noticing that U32 is just going to be that, right? Because it's a distance s away. But the amount of energy stored here due to this one that's going to be the square root of 2s. That's the distance. So let's get the energy for this one. It should be less, right? Because it's further away. So here are the two next terms. The energy due to this charge and that charge together is going to be the same as these two. But the energy due to this arrangement, it's a little further away, so it's the square root of 2s. And so the value is this number divided by the square root of 2. So the total energy now is this, plus that again, plus this. Now bring the fourth charge in. And when I move this to the fourth corner, there's an energy due to its placement relative to this, and relative to that. So you can see the energy of Q4 relative to Q3 is the same as that. And the energy of Q4 relative to Q1 is going to be that. But its energy relative to Q2 is going to be that. So the energy by bringing this one in is actually the sum of all these energies. So the 6 terms are 4 of these and 2 of these. I hope you can follow that. So here's the calculation. There's 4 of these and 2 of these, because there's 2 cross charges. And when you calculate it, you get 509 millijoules. That's for the charge that I'm using, which is just 1.12. So you're going to have a different number. Most likely your charge is larger and the amount will be larger. The general solution, notice that the general solution of this is just k q squared over s. And for the cross distance, it's kq squared square root of 2s. So there's 4 of these. This is a coefficient of 1. And this is a coefficient of 1 over the square root of 2. So there's 2 times that. And if you simplify this, you get 4 plus the square root of 2, which is this number. And so here you have the general solution of the amount of energy. If you have 4 equal charges arranged of magnitude q, arranged in a square of side length s. Okay, the last step is to find the electric potential at the center. Now we're finding the potential, right? There's no charge, so we're going to use kq, just 1q over r. And notice that there are 4 charges contributing, and the charge and the distance is all the same. And since this is the square root of 2, that distance is going to be the square root of 2 divided by 2 times s. So see if you can do that. Do the general solution, and then the numerical solution is easy. Okay, so V at the center is going to be 4 terms, 1 for each charge. And K is K, Q is the charge, and the distance, as we said, is the square root of 2 over 2. That inverts and multiplies to 8 over the square root of 2, which simplifies to 4 times the square root of 2 times KQ over S. So see if you can follow that. And now if we do the calculation, we have the coefficient times the K times the Q, and notice we have 10 to the 9th, and the charge is microcoulomb, so it's 10 to the minus 6. So we automatically end up with 10 to the 3rd, which will be kilovolts. So when I multiply this out, I get 475. For this charge, I get 475 kilovolts side S.